Math 2414, Calculus 2, Section 9.2, Calculus with Parametric Curves, Video 7 of 9, Arc Length. If it feels like we're doing a lot of different calculus things at once, it's because we are. But I've warned you that at this point in any calculus sequence, everything you've seen previously is still fair game. So as we make the transition to parametric equations and parametric curves, it stands to reason to ask, how do we do the calculus we've already done with these new things? So slopes of tangent lines, areas under curves, arc lengths. In fact, the arc length discussion is critical for the development of some techniques in Calculus 3, or multivariable calculus as it's called in some institutions. So we're going to take a look at how to calculate arc length when your curve is defined parametrically. But first, let's recall that if our curve is defined as y as a function of x, then we can calculate the arc length, which I don't know why I put L. I do know why I put L because this author does early on. It's also common to use a lowercase s for arc length, such as in the arc length of an arc on a circle. But to calculate arc length, when we know our function, y is a function of x, we integrate from the first x value to the last x value, or rather the least to the greatest. We integrate the square root of 1 plus the square of the derivative, dx. But how do we do this parametrically? And keep in mind that parametrically, x is a function of t, and y is also a function of t. So what if we have this? Well, we can kind of do the same thing, but we have to first make a concession like we did when we calculated area under a curve in the previous two videos. When you calculate the area under a curve, we're assuming that the curve does not change directions horizontally. In other words, either it's continually moving left to right or continually moving right to left, but doesn't switch between the two, because then we get overlapping areas and things are messy. For arc length, we're going to start the development of this formula under the same premise. Now, it shouldn't matter, because if we have a curve that doesn't change direction, its arc length is its arc length. But if it does change direction, its arc length is still its arc length. In other words, the distance around here, or the distance you travel along this curve, is independent of the fact that the curve turned around. Unlike looking at the area under the curve, where, if this is where we were, the area under the curve is here, but then it doubles when we look under here, because we pick up this piece twice. Once under the curve before it turned around, and once again after it turned around. But it seems like arc length shouldn't have that issue, because we're not looking under the curve, we're just measuring how long it is. And the truth is, it doesn't matter. But in order to develop what we're about to develop, we're going to work on the assumption that our curve doesn't change directions. And more specifically, that it's always moving from left to right. Which means, let's assume just for a second that the derivative of the x is greater than or equal to 0. And you'll see why that's an important assumption to make in just a second. Then what does this mean? This means that the square root of the square is equal to the original. Positive numbers, or rather non-negative numbers, are the only numbers that stay the same after you square them and then square root them. Because think about a negative number, like negative 5. If you square negative 5, you get 25. And if you square root 25, you get 5. That's not what we started with. We started with negative 5. The only time squares and square roots technically cancel is when the thing that you're doing them to is not negative, greater than or equal to 0. So we're going to start with the premise that this derivative is greater than or equal to 0, so that when we square root it square, it comes out to be what we started with. Now, why is that important? Because that means that our integral, which is the integral of the square root of 1 plus dy dx squared dx, I can make some substitutions. For example, I can change, and in fact, I'm about to put this in terms of t. So how can we do that? Well, first off, if our x's derivative is positive and our parameter is going from a to b, then the leftmost value of the parameter is A and the rightmost value of the parameter is B. So let's start by saying we're integrating from A to B. Now, what can we replace the derivative of y with respect to x with? Well, it's a little bit tall to cram inside of this integral, but we can replace dy dx with dy dt over dx dt. That was from the very first video. All right. What about the dx? Well, we can replace the dx with dx dt times dt. In other words, this becomes this. All right, so this is just getting uglier looking, but it's about to get a little bit better. If we replace dx dt with the square root of its square, which we can do as long as we're assuming dx dt is non-negative. Well, let's go ahead and do that here. Replace you with the square root of your square. Why is that important? Because now both of these are living under square roots, so we can multiply them together. How would we multiply them? Well, we would distribute. We would distribute this squared dx dt across both halves of this addition problem. And what would happen as a consequence? Well, this part's easy. Now be careful. When you're distributing this, oh, it is squared, I'm sorry. This thing squared is getting distributed to the 1, so it shows up over here, dx dt squared. But what happens when this squared dx dt hits this squared fraction? Well, if you gave the square to each half of the fraction, gave it to the top and gave it to the bottom, then when this guy swoops in and multiplies by that fraction, it literally cancels the denominator and leaves the numerator, dy dt squared. And just like that, we have the arc length integral parametrically. So, if my parametric curve is defined by x equals x of t and y equals y of t, then the arc length is from the leftmost value of the parameter to the rightmost value of the parameter of the square root of dx dt squared plus dy dt squared dt. In other words, it's the square root of the sum of the squares of the derivatives of the parametric equations. That was a long prepositional phrase, so let me say it again. The arc length is the integral of the square root of the sum of the squares of the derivatives of the parametric equations. Now again, this was built on the premise that our graph was only moving left to right, meaning that our x derivative was never negative, so that we could pull off that little move where we replace dx dt with the square root of its square. However, this is true all the time. It doesn't matter if your dx dt is non-negative, non-positive, or switches between being positive and negative. The proof for it is a little bit more detailed. If you're in the book and would like to see, I'm going to refer you to page 511, where it says, even if we can't go from left to right. And by the way, going from left to right means that y is a function of x, because the graph wouldn't fail the vertical line test. But even if we couldn't do that, the formula ends up being the same. The setup is using a Riemann sum. I invite you to take a look at it. It's not really that hard to follow. But the result is that this is our arc length formula, even if we don't get this. The proof for it is just a little bit more based on a Riemann sum, instead of just taking what we saw originally and did smoke and mirrors and said, poof, here it is parametrically. In the next video, we're going to take a look at an example of arc length. I can't remember if it's about a cycloid or not, but it wouldn't surprise me.